In this lecture, we're going to continue our program of making sure we can do all of the things with our new parametric equations that we could do with kind of the standard rectangular equations. So we're going to start with our usual set of parametric equations, x of t for the x coordinate and y of t for the y coordinate. And our goal is to find a formula for the area under the curve described by those equations. Now, to find that formula, we're going to start with what we already know. In this case, that means the formula for finding the area under a standard function. So to do this, we're going to use an approach that's similar to the substitution method you learned for calculating integrals. First, I'll substitute y of t for y. And now we need to make a similar substitution for dx. Well, since dx dt is equal to x prime of t, this means that dx is equal to x prime of t dt. So substituting that into the integral over here for dx, gives us a formula for the area in terms of our two parametric formulas. And now finally, we need to change the limits of integration. The original function was integrating in terms of x, so the boundaries of the integral were two x values. Since our new formula is integrating with respect to t, the limits need to be changed to corresponding t values, which I'll call alpha and beta. So let's take a look at a specific example here. First, take a look at the equations. Now, we've seen these before, right? They're the parametric equations of a circle whose radius is r. So this is another example of a situation where we know what the outcome should be. So we can use this as a way to kind of test out our new formula. All right, so let's see. X prime of theta is r cosine theta. And if we substitute that in here, that makes the integral from a to b, we'll worry about those limits in a minute here, of r cosine theta times r cosine theta d theta. So if we do a little simplifying, this is the integral of r squared cosine squared theta d theta. Now, we want to get a complete circle. So you might think that the limits here should be from theta to 2 pi. But think about what's going to happen when we cross over the theta equals pi mark. On that half of the circle, we're getting negative heights, right? Which we don't want to do because we've seen this happen before. If we allow negative values when we're calculating an area, they cancel out with the positive values. And in this case, because the two sides are symmetric, it's going to leave us with 0 for the area, which obviously isn't right. So to fix this, we can use the fact that the upper and lower halves are symmetric and just integrate from 0 to pi and then double the result to get a whole circle. All right, so now we need to integrate this thing. So let's see. First, let's bring out that r squared because it's going to be a constant. And then, let's see, how are we going to do this? I'm going to use a trigonometric substitution here to get this integral. Cosine squared is 1, let's see, make sure I get the sign right here. I always mix this up. 1 plus cosine 2 theta over 2 d theta. Okay, and this we can do. This is 2r squared, integral from 0 to pi. I'm going to split the fraction up. 1/2 d theta plus the integral from 0 to pi of cosine 2 theta d theta. Don't forget those d thetas there. All right, so good. Now I can actually do the integral. This is 2r squared times theta over 2 plus 1/2 sine 2 theta. And I'm going to evaluate, I really had an extra parentheses there, didn't I? Then I'm going to evaluate this from 0 to pi. All right, so let's see what happens when I put, and I'm out of room, so let's see. Let me jump up here. This isn't going to take too much more space. This is 2r squared times, if I put pi in, I get pi over 2. And what happens with the sine part? That's 1/2 sine 2 pi. Sine of 2 pi is just 0. Minus, let's see if I put 0 in, theta over 2 is 0. And sine of 2 times 0, that's sine of 0, which is also 0. So what do I end up here? This is 2r squared times pi over 2. The 2's cancel, and look, we got exactly what we expected to get, pi r squared, which we already knew was the formula for the area of a circle. So, excellent. Our formula A is working, and B, we know how to use it. Right? We're using it properly to get the results that we expected. So now that we have that formula in hand, we're going to, in the next lectures, calculate the corresponding formula for the arc length of a parametric curve. And then we'll look at some more detailed examples and see how each of these formulas is used in practice.